Okay, good afternoon. Hope you all survived spring break and are well rested again and dying to hear more about computer systems. So what I'm going to talk about today is fault-tolerant computing in general. And this is going to be a series of lectures about fault tolerance and security. So you will see that basically the rest of the semester, our main challenge is going to be dealing with failures of different types. Just to remind you where we are in 6033. Remember, before spring break, early in the semester, we introduced this model of client-server computing as a primary mechanism to isolate faults. So that if a fault happens in the client or in the server, we limit propagation of those faults. They show up as an error, but at least they don't fail either the client or the server. And we've looked at two different implementations of the client-server model at a very high level. One within a single operating system. If you have the client and the server running in the same machine, how to get strong fault isolation. And then, of course, running the machines running the client server on different machines, connected by the internet, which gives you another sort of much stronger form of fault isolation, because the machines can fail independently. And clearly, this is a good starting point for building fault-tolerant systems, but we have missed two limitations that we actually have not addressed and that we're going to try to address. One is the errors that we were isolating in the client-server model were mostly benign errors, programming errors that caused an independent module to fail. And we want to look and sort of try to broaden the set of errors that we're going to be covering, including, if you will, malicious errors, errors introduced or triggered or tickled by attackers. The second part that we really haven't talked much about, and we're going to talk quite a bit about, is how to recover. If a client or a server returns an error, what we're going to do. Right? And so far, we basically have assumed that they return an error, and then it's up to some other module to deal with it, or even repropagate the error to the user, which is not an uncommon way of doing things. Think about serving web pages. And if a server fails, you might just see a web page that says, server not responding. But for certain systems, we want to do quite a bit better. And so we'd like to be able to design a system that we can keep computing despite failures. We've seen this a little bit in one example, for example, when we talked about the MapReduce paper, which allows, even when machines fail, the MapReduce jobs actually all get run. And so how can we sort of generalize that kind of idea to actually more broader set of applications? The other class of failures that we'd like to deal with is defending against attacks. And we can think about those as malicious errors, a sort of very strong form of an error. And so the rest of the semester is just going to cover those two topics. Fault-tolerant computing, dealing with machine failures, component failures, et cetera. And then the second part or segment of 6033, which is completely focused on computer security, dealing basically with attackers. So the plan for fault-tolerant computing is as follows. It turns out this topic is quite tricky. It's not that straightforward as you might think. And it partly has to do with, it's not sufficient to come up with a design to sort of show that it works in a particular case. You have to argue that your design works in all cases. And particularly the cases that are difficult are where the error happens at the most unfortunate time, where the machine fails at a point where you were hoping it was not, or your design was assuming it was not, and you still have to recover correctly. So today I'm going to lay it out in very broad terms. I'm going to talk about redundancy, recovery, replication, and just the general way of building fault-tolerant systems with a couple examples. And then next 4 lectures, we're going to focus on transactions, which are a very good building block for dealing with permanent state while at the same time we have concurrency errors and we have failures. And then finally, we're going to talk about, this allows us to cleanly recover after failure. And then finally, we're going to talk about actually how to keep running, while machines are failing. And so that, using an approach that's called replicated state machines. Okay, so that's sort of the broad outline. And so, returning to, just, the kind of failures we need to deal with. So, you probably have seen this, at some point. One used to see this quite a bit, right? Your operating system crashing. And that's only one set of failures that you may want to defend against when you build a fault-tolerant system. So it's worthwhile talking a little bit about what kind of failures or faults you want to deal with. Clearly one class is software faults, and another, like the ones like the blue error or the blue screen, where you have a programming error inside your operating system or inside your kernel. You divide by 0, or you dereference a wild pointer, and the computer crashes. Similar, we want to be able to deal, of course, with machine failures. There's a power outage, or somebody trips over the power cord, or some component of the machine fails, and the machine just dies. Those are sort of the obvious one, but a couple other ones that we worthwhile thinking about while we are going through this process of designing fault-tolerant systems. One is that there's another class of design errors. Clearly, design has to be done pretty well if we have the system to be fault-tolerant. And so any errors in the design, is going to probably lead, to failures of the system. And so clearly doing a good job at the design is going to be very important. And we have seen plenty of examples, in 603 so far, where that not always has been true. Right? The one that probably stands out most in this department is the Ferric 25. Another two classes to consider when designing fault-tolerant systems are operational areas. So even if you got the software right, the machine right, the design right, you might actually be operating the machine or the system incorrectly. And we've seen, mentioned briefly at some point that there was a big internet outage when somebody misconfigured the BGP servers, advertising the wrong routes. It used to happen periodically happens, where some fragment of the internet gets disconnected from the rest of the internet. And so operational errors are a very common source of failures, and if we want to make our systems fault-tolerant, we have to think about those. And then the last class are environmental errors. And so here I'm thinking about earthquakes, tsunamis that maybe knock out whole data centers or parts of a country. And if you want to build a system that survives even those, you really have to think carefully how to do this. Right? And in many ways, the core internet design, the packet switching, was based on with the idea in the background we have that you wanted to support systems where large fractions of the internet could just disappear, and you still will want to be able to operate. So keeping those failures in mind, makes clear, first of all, what the challenges are, and two, you can sort of later go back and sort of see how well did we deal with the particular classes. Now, one way to design fault-tolerant systems is to say, well, what I'm going to do, the approach I'm going to take is I'm going to take every component, whether it's a machine or the software that's running on the machine, the way the operations is done. I'm going to try to make it perfect. There's no way it can fail. Like, I'm going to prove every line of my code correct. And in the end, I'm going to conclude that there's no way that can violate the spec, and therefore this component is completely fault-tolerant, or it will be good. And certainly that's possible, and certainly people try to go in that direction, but it's not the approach that we're mostly going to be discussing in this section of fault-tolerant computing. And in general, the way we're going to think about the problem is what we're going to try to do is actually sort of slightly different. We're going to try to provide reliable systems out of unreliable components. That doesn't mean that every component is so unreliable that you can't use it. We're sure going to try to sort of put our best effort into making the components work well, but we're not going to try to shoot for perfect. And the reason to do that is generally designing for perfectness is very, very expensive to do. And second of all, it's likely not to be perfect, because even if let's take the software proving case. Even if you could prove that your program was completely correct and actually implemented the spec might be wrong, right, in certain cases. And then if it's part of a larger system, how to handle that. So we're going to take this approach. This is a pretty standard engineering approach of trying to build the systems out of unreliable components. And we already have seen a number of examples along those lines. So, for example, the DNS, right? Which you're doing it hands-on for tomorrow, but we have seen that servers can fail, and the design of the system is done in such a way that even if some of the servers fail, or one of the replicas of the root server fails, the system actually will continue running. And it's carefully done in that way. And so here's an example of a reliable system built out of unreliable components. It's just designed to handle server failures. And we've seen a couple more examples. BGP deals with routers going down, deals with network paths not operating by choosing different network paths and responding to failures. Right? There's a good example. An even simpler example is TCP. Right? It deals with the fact that actually the packet, that the network is not perfectly reliable. It actually handles packet failures, out of order, duplicate delivery, all that kind of stuff. Right? It's designed, to actually do this. And in fact, we've seen that basically the internet is not a perfect network. In fact, this is a pretty, it has a pretty low quality of guarantee, if you will. Right? It just does best effort in terms of delivering packets. So the general approach in building fault-tolerant systems is to be pretty careful and state very explicitly what your assumptions and goals are. And so the typical rail when one builds fault-tolerant systems is, first of all, identify all possible faults. Think about them and decide whether you actually want to deal with them. And so the first, if you decide you want to deal with them, you actually have to be able to detect them and isolate. Now, once you've decided you want to deal with them, you have a mechanism to detect them and isolate them or contain them. Then, of course, you need to decide what to do with them. And so there's a couple options, in terms of handling. The first thing one option is actually to make the system or a component that has a fault fail fast. And this means that the component, if it detects actually internally an error or a fault, what it will do, it will generate an error on this, or return an error code on this interface as quickly as possible. Right? And so you're pushing the problem to somebody else, and then you have to have a higher level plan. But you have to have, if you design a system like that, it has to fail fast property, you have to be able to argue, okay, I picked all up the faults that I want to deal with in the fail fast approach. I'm good to be able to detect them, and I will return an error in all cases. Another approach, which is actually quite common, is fail stop. As soon as a component detects an error internally, it just stops and doesn't do anything in there. It does not return an error, but just completely stops. And the reason typically to do that is because it might actually be hard to return an error if you have internal state in your component is not correct. Maybe you return the wrong error value or something like that. And so a common approach is actually to just, right there, stop doing anything. And that, of course, returns, if the system is set up in the client-server style, the client will notice that the server is not responding and that can react. So you can think about this as an indirect way of returning an error code. And the final thing that we can do is actually mask and come up with some plan that actually allows us, to mask the failure completely. Right? And if you think about these particular cases, like in the case of TCP, right, the way masking is done of a packet failure is by just resending it. Right? And the way actually that, let's say packet actually is change of content, the way that is detected by some redundancy in the packet, correct checksums, and to verify by the receiver or the sender whether actually the packet is still valid. Right? And so this is a way of detecting and then isolating the property. Okay, so that's the general approach that we're going to take. Now, often, once you actually have done this and you built your system and you put the system in place, you will discover undoubtedly that you didn't really didn't really think about all possible cases, and you might actually observe that the system actually does fail. Right? Even though you did a perfect job, you probably should assume that you might actually have slipped up somewhere. And so the general theme here is that when you do a failure, once you've got a failure and it was actually not expected and you have no way of handling it, you've got to go back and sort of look at that and say, okay, well, where does this, in what class does this error fit? Did I identify it? And if not, I should now identify it. And what is the right way of identifying? Should I detect and isolate it? And should I handle it? What should I do for future cases? Right? So this is sort of an iterative approach. And then systems that have a goal to be actually highly fault tolerant, take this approach extremely serious. Right? Like you think about the airline industry, right? Like every plane has a black box, so that and later on, when there actually was an unexpected failure, you can go back, look at the data in the black box, figure out what's going on, and perhaps issue warnings or instructions to the airline industry for the particular manufacturers to do a better job at a particular component. Right? And that's the only way sort of we know to try to do sort of get to really highly fault-tolerant systems. So this approach of like going back and looking at a failure and studying it very carefully, like for example we did in the FAIRC 25 case, is essential, correct, into building fault-tolerant systems. Okay, so a couple words on terminology, and that's helpful to think about. So we have a module. So let this module M1, and M2 uses that module. And we have somewhere in the design of the system a fault. It's going to, maybe it's a programming statement that actually computes something incorrectly or divides by 0 in particular cases. If that fault is not triggered, we call it a latent fault. If it is triggered, for example, some input, result that line to be executed and results in division by 0, we call the fault active. Now, an active fault can result in an error, for example, division by 0. But that's still internal to the module. And now, what we're going to call a failure, if this internal fault that triggered an error, if that actually error is visible across the interface between module 1 and M2. And so if M2 can actually observe this internal error, and that may be because it was a fail fast system or a fail stop, then we're going to say that actually error turns into a failure because it's observable to an outside module. Now, for that particular module, what does that mean? Well, for that particular module, that internally, module, the way to think about it is for that module, that is just another active fault that that got triggered. In itself, that might show up as a failure to a third module, right? And so this is sort of like how we distinguish between the different terms of fault, errors, and failure. So failures are visible in the interface, errors internal to a module. A fault is actually something that's wrong and that might trigger into an error. Now you will notice that I'm incredibly sloppy with this, and I sometimes actually interchange the terms, but this is sort of the official set of terms to be used. Okay. So having laid that out, now once we have sort of approach, laid out. We're going to design system out of unreliable components. It's useful to actually have a metric about like how good did we do. And that metric, is typically called availability. And it's based on the following observation. Let's say we have a system that runs successfully for a period of time, and then it actually has a failure. And then we call that period between failures the mean time to failure. Then there's a period of time where the system might be unavailable because it's being repaired, and we call that the mean time to repair. And so the system goes for these cycles of failures, repair, etc. Right, and now we can easily talk about a definition of availability. We can just say, well, when is the system available? Well, clearly in the period between the two failures. So availability we can measure the availability of a system as the fraction of the mean time to failure divided over the mean time to failure plus the mean time to repair. Correct? It basically says, of this fraction of time, which time is actually the system up and running. And this mean time to failure plus mean time to repair is sometimes referred to as the mean time between failures. Okay? And so, in fact, people in practice, measure, the availability for systems. So here are some common numbers. So clearly, the airline, as I talked about earlier, the airline industry is very serious about this and keeps very careful track, and claims a 90.99993% availability. And so typically, actually, when these systems are judged, in terms of the availability, we talk often by the number of nines. So the airline industry sort of achieves, in terms of designing systems, 5 nines. This is a comparison, the 911. Clearly servers that should be available a lot, and is also carefully tracked and measured and analyzed, et cetera, and is reported to have 4 nines of availability. A standard phone service, because this slide is slightly, what is a standard phone service? This is landlines, before we had wireless, and everybody had cell phones. And the phone industry also did a serious job of sort of measuring the availability, because if you pick up the phone, it'd be nice if you dial a phone number, somebody else picks it up on the other end, correct? The phone at least rings. And they measure outages in terms of the number of minutes per year. And you can see that it achieves in the 4-9 sort of sign. Achieving that kind of reliability or availability, correct, is very impressive. It requires a huge amount of engineering to get that kind of. The internet is substantially lower. So connecting making a TCP connect, this looks at the question of like end hosts trying to make TCP connections with each other, and is in the order of 1 to 2 nines. All right, so it gives you a little bit of a sense, what the what the ranges are. So what I'd like to do in the rest of the lecture is actually focus on the reliability of one component, namely a hardware disk. We talked a little bit earlier about it, and it showed up indirectly in the design projects, but I want to talk a little bit more about the reliability of disks. And the reason I want to do that is because they're sort of the building blocks for actually building fault-tolerant software systems. So if you think about a fault-tolerant system, software systems, when you have a computer, operating system running on top of it, a bunch of processes, P1, P2, and we have our disk. The way these systems are typically organized is going to have a plan for what happens if the power fails. And one of the attractive properties, correct, of a disk is that it actually stores its state after a power failure. It can store state persistently. So the typical way you build a fault-tolerant system, software system, is to say, well, I got two pieces of state, split all the state in one that is the crucial or important state. And of course, what you want to do with the important state is you want to store it on disk. So if the machine fails, you can back up and you can look at your disk and say, okay, well, there's my state, and I can recover from that state. That's why we store the file system on the disk, right? It'd be pretty annoying every time you had a power failure, all your files are gone. And I guess then the temporary state that may be necessary to run the computation, like the inalternate state of registers or whatever, but that's actually not crucial in terms of surviving a power failure. And so the model is, for this stuff, it doesn't really have to be on the disk, but this stuff actually has to be on disk. And a very simple way of doing this, right, that we have seen is, for example, you take a virtual machine, and once in a while, you checkpoint it. And you write all the state to its disk, so that if you have your failure, then you grab the latest checkpoint of your virtual machine. I'm sure you do this on your laptop once in a while, and you can start the virtual machine from from the last checkpoint. Right? And all your computations, everything, bomb is back up and running. Now, that's not a particular efficient way of doing things, because you actually have to write a complete checkpoint to the disk. And we'll see in the next set of lectures that most systems are much, much more carefully about what they're actually writing to disk and try to write as little as possible, but enough so that they can reconstruct the state after a failure. Right? So it makes sense? So we're pretty interested in the reliability of disks, because if they are not very reliable, we have not a great stepping stone to start building up real systems. And clearly, an internal disk is quite complicated, correct? There's platters. Let's see if I can make this work. There are platters here, correct? There's the disk arm that seeks to do the appropriate cylinder to read a disk block. There's a controller that runs a piece of software that activates these arms and the mechanical components. Right? So it's not actually, if you open it up, it's actually a pretty interesting system in itself. And so we can think about how good it is. And if you look at the vendor specs for a disk, they actually do quote this mean time to failure number, or mean time between failure. Right? So this terminology of mean time to failure and mean time between failure is a standard terminology everywhere used in the fault-tolerant literature. And in fact, if you look at DiskMedisk, there's a low-end disk, that quotes 700,000 hours. And if you look at a little bit more, high important disk, they're called business critical, then it's like 1.2 million hours. So how much is 1.2 million hours? Divide by 24, divide by 356. How many years? I did it for actually the 700,000 one. I didn't do the. But you. Sorry? How many? 6. Yeah, 136. Thank you. So that's impressive, correct? 136 years. But how did they measure that? Were there disks 136 years ago? Not really, correct? So what is the method? We should try to understand what this actual number means. So the way this typically is done is not wait for 156 years and then count the number of disks that are actually still running, but you take, say, a bunch of disks. Let's say you take 1,000 disks. You run them for 3,000 hours. Say, it's still a lot. There's a substantial amount of time, correct? But certainly, you can wait on that. And let's say you observe. Here's an example. And let's say you observe 10 failures. And so you can then basically say, well, the failure rate, correct, is 1, over 300,000 hours. Right? And then you can say, well, so I did this for, these 1,000 disks. Now let's just assume for a second that, I run them again for 1,000 hours, or 300,000 hours. And if this process is memoryless, correct? I didn't know whether it was the first batch of 3,000 hours, the second or the third or whatever, then I should observe, again, 10 disk failures on average. And so I still have a failure rate of 1 over 3,000. Right? So if I assume that the process is memoryless, I can just say, well, the mean time to failure, between failure, is going to be 1 over my failure rate. Right? And that's going to come out to 300,000 hours. Right? So, but that make that assumption that this process of repeating the 3,000 hours is actually memoryless. And that, of course, is not true. Correct? If you look at disk failures, and this actually turns out to be true for many, many components, they follow what's termed the bathtub curve. And that basically says there's a period of time where you produce a set of disks and an initial set of disks, and that period of time is called and the number of disks fail in that period of time. They're this is the internal testing that the manufacturer might do before shipping it, just making sure. And it could be like they produce a whole batch that's wrong, right? There's something went wrong with the production, and so they die, early on. They're called infant mortality. And then there's a period of time, we get out of the infant mortality period, and then there's a period of time where basically, this is the low end or the bottom of the bathtub curve. And so here things are actually operating in this sort of 3,000 hour period, and that is exactly where we're computing, where the disk manufacturers compute their mean time to be failure here. But then at some point, the disk might actually age, and then presumably the number of failures actually goes up. And so the process actually generally typically not memoryless. I mean, if you run them for long enough time, the number of actual failures tend to go up quite dramatically. Right? And so aging typically actually is a real issue. Now we know that aging is a real, so this period of time, correct, once it actually gets past its lifetime, it's typically called the burnout period. And we know that aging is a real issue, correct? If we look at humans, they have a similar curve, correct? The bottom of the tub is not that long, but the failure rate comes up with aging. And it turns out with disks, this happens too. So this is a graph, where a bunch of people measured this, and if you run the number of disks, for a number of months, there might be for the first couple months, correct, it's pretty low, but then actually starts dramatically increasing. Okay? And so aging is a real issue. And in fact, there's another study done by a bunch of people that went actually into a number of several data centers run by different companies, and they looked at actually what failures actually happen in practice. And they actually find out that for a particular machine at company one, hard drive failures count for about 18% of the machine failures. Okay? So it's actually interesting for us, to figure out, to do a good job, correct? The disk is not perfect, and we want to monitor it sort of carefully and design systems that can deal with at least with some certain types of failures. So I'm going to talk a little bit about sort of the internals of the disk and see how you can make them actually reasonable fault tolerant. But to do that, let me first show you sort of a slight little demo and look at a real disk in action. Is this readable? Hopefully it is. Let's see if I still have, okay, I still have internet connection. So I'm going to, there's a program, I logged into a machine somewhere up on the 9th floor that has a disk attached to it, and there are programs to, yeah, go ahead.
Can you bump your font size?
Give me a little bit more?
Yes, please.
Is it better? A lot more. How about this? Keep going. How about this? This? And one more. So there are programs that allow you to look at the health of your disk, correct? Because you want to know whether you're in the are you reaching the burnout period? Because if you reach the burnout period, you better start copying your data off your disk, correct? If you particularly want to build fault-tolerant systems, and all your really valuable state is actually sitting on your disk, correct? So we can look at this and run it. Actually, that's not what I wanted to do. Sorry. Give me a second to scroll through my commands and, okay, good. So I'm going to run it and look at the output for a second, and so see what we actually get. So this program talks to the disk controller, and the disk controller maintains all kinds of state about errors. So it says like raw read errors, the seek errors, spin retry. So a whole bunch of statistics that it actually maintains. Right? And so we looked at it and we read something from the disk. We can run it again and compare what has changed. Right? And we see actually, even though we actually didn't really use the disk heavily, there actually were a bunch of different seek errors. So remember, the way the disk works, the seek operation is moving that mechanical arm across the disk to the right cylinder. And the disk is spinning, at a lot of rotations per minute, like 10,000, correct? And so it is actually a pretty tricky operation, and basically when there's a seek error rate, it means that the controller sort of failed, to get it on the right cylinder and has to basically adjust and recalibrate and retry. Okay? So now let's actually run some big thing that actually scrunches over the disk for a while. Actually, let me do it not home, but so I read a lot of things. So let's see actually what comes out of this. Oh, that was not such a good thing to do. Let me something bigger. Good. That's gonna. Okay, great. So hopefully this is scrunching over the disk a bit. And let's look at it again. Oh, I'm unlucky today. So I was hoping to see a whole bunch of different errors. And every time I've done this demo or tried this out in the last couple days, which is many times, what shows up actually is that a number of times it tried to read a block, and it found actually that there was a permission, that there was a checksum failure. So the block didn't check out, so the read was unsuccessful. But the disk maintains a bunch of error correction bits, and it was able to reconstruct, from the error correction bits, the correct data. And so let's see if I. In addition, of course, you see more seek errors, and. Oh man, that is so annoying. Let me give this, let's see what else is on this machine. It's probably sitting in the buffer cache for a part, and I'm not actually using the disk. Okay. Good. So now you see, correct, we see a whole bunch of things that changed. We see this, there was a number of changes in the number of raw read errors. In fact, we had this is pretty cool. We do actually have a real raw read error, which I hadn't seen before. We see a bunch of seek errors. It also gives you a bunch of, you see that the temperature fluctuates a bit. And this is important because it's well known, like if you overrun the disk with a too high temperature, actually the errors tend to go up. And we see also a couple cases where actually there were hardware ECC recovered blocks, correct? And so you can use these statistics, to look at your disk and say and monitor it continuously, and this is why this program exists, and sort of take preventive action. Now, but you also see that clearly indicates that the disk actually is doing all kinds of interesting stuff inside the controller itself, correct? And so let's think a little bit about, how that actually might work, and build sort of a slightly more, sophisticated disk from basically the pure platter. So let me go back to my slides. And so the first thing, it actually clearly what the disk does internally, it actually tries to the controller, plays a game where it tries to detect errors. So it has a plan, correct, for identifying errors and then actually do something with it. In the simplest case, it wouldn't do anything, right? It would just get the block, as in this slide, get the block, compute the checksum of the data that it received, correct, the controller, compare it to the checksum that actually is stored in disk, and if they're different, we know there's something actually been wrong in transferring the bits from the platter into the memory of the controller, right? And so in that case, we could return an error. we actually see that the disk, that we're really just looking at does something more sophisticated, correct? When it actually sees a checksum error, it tries to reconstruct the block from the error correction bits that are also sit on the platter, correct? And not only that, it actually retries, a couple times, before actually giving up. So, for example, in the case of a seek error, it tries to read the block again, the controller internally, before actually trying to give up. And so this is a typical thing, where the disks are layering a number of mechanisms on top of each other to build a more and more and more reliable disk. Right? Now, of course, you could get, this gives you a little bit of more reliability, and at least allows you to detect, bad blocks. It allows you to repair bad blocks in certain cases. Of course, you lose out when both the error correction bits are wrong and the data block is wrong. Right? And so typically, if you're really serious about fault-tolerant storage, you go one step further, and actually you can start replicating the disks. Now, if you do this in a naive way, it's going to, if you want to replicate a complete disk, you need 2 disks, right? Which means like basically your half, sort of one way to think about it, your utilization, your effective utilization of your disk space is only 50%. Now, on Thursday, you're going to be reading a paper that actually does a much better job at that. Right? And so now I'm not going to spill the beans right here, but just to point out that even though we're going to sacrifice 2 disks for more fault tolerance, we can actually do better. And you should read and that'll be the topic of Thursday's section. But then the way to think about it, what the controller does, it writes the block to 2 different sectors on disk, correct? And then when you do a read, you read it first from the first disk using the careful get, which basically automatically corrects error correction bits, recomputes the checksum, even retries a couple times, but it really can't actually read the disk block, and we'll try to read it from the second one. And if there's no error, then we actually have 1 valid block. Right? Of course, we need also a recovery procedure, right? If actually block or disk goes bad, we should try to repair it, because otherwise, we only have 1 copy of a particular block. Right? And so, in fact, to doing this all right is actually quite complicated. And in fact, the disk controllers or the disk systems that do it right contain a lot of components. In fact, the internal paths between the controller and the disk have to be duplicated. They have to run with additional power supplies. You have to run with additional fans. And so if you look at the spec, one of these sort of more complicated, internally high reliable disk systems, they're tremendously impressive. Multiple CPUs, as you can see here. It has N+1 power supplies, N+1 fans, et cetera, et cetera. This is a complete BV, computer, correct? In fact, it has 2 to 16. It has a couple Intel Itanium processors sitting inside of it. Right? And so, actually, doing a really good job of building these systems is tremendously complicated. But it can be done, right? And this completely follows this philosophy of trying to build reliable systems out of unreliable components. By using replication, not only for the disk platters, but also for the internal networks, for the internal power supplies, for the internal fans, et cetera, et cetera. Now you might wonder, what about an error in the software, correct? This disk controller that's going to be sitting inside of that, this is a reasonable complex program. And particularly if you include all the things that we're actually you're going to be reading about on Thursday, correct? And so any error, let's say there's actually an error, a bug in the fail fast get routine function, correct? That would be a disaster, right? Or there actually the internal disk software does a divide by 0 accidentally somewhere. Basically crashes the system, right? And this is our high reliable fault tolerant system from which we're going to build further fault tolerant systems. So it'll be a bad thing. So it better be the case that the internal software is very, very correct. And that turns out to be extremely difficult to get right. And so the way this typically is done is to follow very stringent development practices. Spend a lot of time on actually careful specification and then implementing software. Try to prove that this implemented software meets actually the specification. Doing modeling and verification on the specification to figure out whether the actual specification is right, et cetera, et cetera. If you're really, very serious about this, and probably people don't do this for internal systems, but they do this for, rocket systems. You actually have 2 different teams implementing the same software. Right? So this is replication of people, of programmers. It's the same idea. Programmers are unreliable, so we duplicate them. Right? And you have to, they write a separate piece of software, and hopefully, you run both of them, and if one fails, then you run the other one, and hopefully the other one didn't get it wrong. And it turns out, of course, two teams of programmers are not completely independent. First of all, they typically start from the same specification. So if there's a bug in the specification, then you're lost. And more interestingly, often programmers make the same mistakes, right? And so there's actually not independence of failure. So this approach is not really used. Inversion programming is incredibly tricky to get actually right, and people don't actually use it that often, as far as I know. Now, we'll see that the same problems, the challenge of building software correctly is going to be hugely important for building secure systems, right? Because the internal, the critical security part of the system better be correctly programmed, so that it doesn't miss access control list checks or anything others that can go wrong. And so, again, the same issue will show up. And the key, way that people actually really go about this is to sort of separate the software in two pieces. The one piece that is not important for security or reliability, and the little, or hopefully much smaller piece that actually is crucial to the security or reliability. And in the security world, it's called the trusted computing base. And you spend a ton of energy on getting the trusted computing base right. And in some sense, we have seen that idea before, right? Like if you think about an operating system, the user level programs can just fail. We don't really care about them. But the kernel should not fail, right? And you can think about, the kernel as the TCB of, a larger piece of software like the operating system. And by minimizing the lines of code, hopefully, you make fewer errors and you can reason more carefully. All right? So that's a general trick, of building, or at a very high level, that's the general approach to building more fault-tolerant software. Okay, so I'm going to stop here. So to summarize, the key thing to remember is that there's a general metric to actually measure availability, that our approach is going to be building reliable systems without unreliable components, and that important building block in actually building fault-tolerant systems is actually persistent storage and disks. And I'll talk about Wednesday. I'm going to talk a lot about how to use that persistent storage in a way that you can actually build systems that allow you to recover. Okay? I'll see you on Wednesday, and good luck with the hands-on.